Hey guys, in this video I'm going to talk about Lagrangian mechanics and give a brief introduction into this somewhat mysterious formalism. I bet you are familiar with Newton's law of motion. Let us have some refresher on this law. The Newton's first law is essentially a statement of inertia. An object of mass m will move at constant velocity unless there is an external force. Newton's second law defines this force as the rate of change of momentum of a system of an object. Finally, the third law states that every action has an opposite reaction. This is closely related to the conservation of momentum. Let us take a look at an inclined plane problem and let us use Newton's law of equation to solve this. As you can see here, I have identified for you all of the forces involved in the system. Then we use Newton's second law to obtain our equation of motion. It seems easy enough, right? But can we do it for a more complex systems, like the double pendulum, or a ball rolling on a very complicated potential? Well, yes, you can use the Newton's law of motion to obtain our equation of motion, but it is very hard to keep track all of the forces involved in the system at all times. It is computationally tiring and troublesome. What if I told you there's a better way? This is where Lagrangian mechanics comes in. Here we define a new quantity called Lagrangian, where it is defined as the difference between the kinetic energy and potential energy of the system. I won't derive for you why this works in this video. If you guys want a video on this, I will make a video. Okay, let's move on. The heart of soul of Lagrangian mechanics is the principle of least action. So in here, I define a quantity called action S, which is essentially an integral with respect to time of the Lagrangian. So as you can see, I have drawn the coordinate system with the same endpoints. So you can imagine there's a lot of different paths to go from the first point and to the second point. But there's only one true path that will happen, which minimizes the action. So we can essentially find the minimum point of S without going through the derivation. We would arrive to this Euler-Lagrange equation. Alright, let's revisit the inclined plane problem. But in here, we're gonna use the Lagrangian formalism. First step, you have to write down what is the Lagrangian of that system. First, let's find the kinetic energy. Kinetic energy in two dimension will be 1 over 2 mx dot square plus y dot square. It's essentially equal to 1 over 2 mr dot square just by Pythagoras theorem. U equal to mgh. So h is equal to r sine theta by geometry. And this Lagrangian, we will end up with this Lagrangian. So just by applying the Euler-Lagrange equation, we will actually arrive at the same equation of motion as we did when we used the Newton's law of motion. Well, you might ask, it seems complicated to use Lagrangian for this problem. Well, yes, because I chosen a relatively simple example. If we had to choose a complicated example, Lagrangian is very straightforward. The framework that I outlined you just now would essentially apply to a very complex system by choosing a correct coordinate system. But for the Newton's law, you have to identify all the forces at all times. But for Lagrangian, as long as you can write out the Lagrangian of that system, you'll essentially solve you'll essentially solve the problem, and the equation of motion is a matter of writing out the algebras for it. As you can see here, we have some advantages of Lagrangian over Newton's. Lagrangian works with scalars rather than vectors, so we don't have to worry about the direction of the forces involved. Lagrangian is easy to incorporate constraints because you can just choose the appropriate coordinate system and just put it in a Lagrangian. And Lagrangian avoids the discussion of force of constraint. As you can see with that the inclined plane problem using Newton's law, we have to know what direction does the normal force acts. While when we are using the Lagrangian formalism, the force, the normal force, we don't even talk about it. Isn't that great? However, there are some downside to Lagrangian. The very advantage of the Lagrangian is its disadvantage. Let me explain. For engineers, knowing and discussing the force of constraints is very, very important. For instance, if you have a support which has these normal forces, we have to know how the normal forces act on the material so that we can choose a material that is suitable to that applications. We have to know the magnitude and the direction of it so that we can identify which material can withstand that force. As you can see, all the classical mechanics problem, all the material can withstand all forces, but in reality, different materials will have different strengths. So it is very important that the engineers know all of the forces involved at all times. So that's why normally in engineering curriculum, there won't be discussion on how to use Lagrangian mechanics, only in the physics curriculum. Okay, thank you guys for tuning in this video. I hope you guys get some idea on this wonderful yet kind of mysterious Lagrangian formalism. Let me get guys, let me know in the comments if you would like for me to discuss more on the derivation of the Euler-Lagrange equation or the principle of least action. Thank you guys, and see you in the next video. Peace out.